So let us look at this final part about finite fields, which is constructing finite fields of quadratic size. So given any prime p, how do you construct finite fields of size p square? Okay, so as we had just seen before, if you want to construct a finite field of size p square, then what we have to do is we have to find a monic irreducible polynomial over fp with degree equal to 2. What does that mean? We have to find a monic irreducible polynomial degree 2. That is, we have to find a quadratic irreducible polynomial, right? Monic quadratic irreducible polynomial, and then quotient out with that, and we'll get a quadratic finite field. That's why it's called a quadratic finite field, because these finite fields are of the form fpx mod ideal generated by a quadratic irreducible polynomial, monic quadratic irreducible polynomial. Okay, so how do we do that? For any prime p, so the case p equal to 2 and p equal to odd prime are different. Okay, so let's first start with p equal to 2, even prime. So 2 square, which is 4. So we construct the field f4. How do we do that? We already know f2 is z mod 2z. Okay, and you want a quadratic irreducible polynomial over f2. Okay, and this is the choice, the polynomial x square plus x plus 1. In fact, this is the only choice. You can check that this is the only quadratic irreducible polynomial over f2, but that's okay. You can check this. So this is the polynomial we take, x square plus x plus 1. Why is this irreducible? Because f2 has two elements, 0 and 1, and this is quadratic. So it is irreducible if and only if it has no roots. Okay, so neither 0 nor 1 is a root of x square plus x plus 1, because you put x equal to 0, it gives 0 plus 0 plus 1, which is 1. Put x equal to 1, it will give 1 plus 1 plus 1, which is 3, but mod 2z, 3 mod 2 is again 1. Okay, so 0 and 1 are both not roots. So this polynomial has no root in f2, and therefore, so what I just said, you can check once again. X square plus x plus 1 is irreducible in f2x with degree 2. Okay, so by just what we saw earlier, when you mod by the ideal generated by this polynomial, this is isomorphic to the field f4. Okay, so f4 is f2x mod ideal generated by x square plus x plus 1. This was easy. Now, when p is not equal to 2, when p is an odd prime, things are a little bit more complicated. Okay, one has to do a little bit more work. So now let us construct finite field of size p square, fp square, okay, where p is an odd prime. And we already have the field fp, which is z mod pz. Okay, so what do? We need to find now a quadratic irreducible polynomial over fp. How do we do that? Okay, so there is no single choice, there are multiple choices, but we need to figure out how to choose them. Okay, so in order to do that, we will consider this map, which I call S, which is squaring map. Okay, it takes the square of all elements. The squaring map from fp to fp defined by S of a is equal to a square. Okay, it takes the square of elements. So what are the things we have? Well, we know that S of minus a, which is minus a whole square, is equal to a square. That is S of a, right? S of minus a equal to S of a. Further, since p is odd, the field elements are also nice. Minus a is not equal to a for any non-zero a, since p is odd. Okay, check that. Because if minus a is equal to a, then 2a is equal to 0. But if a is non-zero, then 2 should be equal to 0. That happens only in z mod 2z. Okay, so since the prime p is odd, minus a is never equal to a for any non-zero a, and we use this property. Okay, so now we can list down the elements as this. So fp, which is z mod pz, can be written down exactly as these elements. So instead of writing them down as 0 to p minus 1 or 1 to p, we are writing them down as 0 and then positive elements and negative elements. Okay, So Z mod PZ will have 0, then it will have 1 and minus 1, then it will have 2 and minus 2, right? But how many such elements are there? Well, there are total P many elements. Now you can take out 0, so remaining elements are P minus 1 many. The remaining elements are both in plus minus pairing, right? So P minus 1 by 2, P minus 1 by 2 many elements on each side. Okay, so it is 0, then 1 to P minus 1 by 2, and minus 1 to minus of P minus 1 by 2. These are the elements. Okay, this is another way of writing down the elements in Z mod PZ. Once we write down this, what do we see? S of 0 is equal to 0, squaring map, and S of j is equal to S of minus j for any j between 1 to P minus 1 by 2. Okay, because of the property of squares. So how many squares are there? How many squared elements are here? Can you guess? So any S of j is equal to S of minus j, correct? So when I look at squares of non-zero elements, I don't need to look at both sides. I only need to look at either the positive side or the negative side. So I look only at the positive side and that is enough. Okay. So the number of squares in FP is the image of S under this map. Image of S of FP. But that is equal to the number of elements here, S of j going from 0 to P minus 1 by 2 because it is S of 0. And then just S of j for j going from 1 to P minus 1 by 2 because S of minus j I don't need to look at since it is equal to S of j. So what is this set? S of 0 will contribute 1. And S of j for j between 1 to P minus 1 by 2 will contribute P minus 1 by 2 many elements. So the number of squares in FP is equal to this, which is equal to P plus 1 by 2. So these are the number of squares in FP. So what are the number of non-squares? Elements which are not squares of anything. Okay, that is equal to size of FP minus the image S of FP, which is P minus P plus 1 by 2, which is equal to P minus 1 by 2. Okay, but since P is an odd number, P minus 1 by 2 must be greater than or equal to 1. P is an odd prime, so P has to be greater than or equal to 3 and P is odd. So what does this say? This says that there is always at least one non-square element in FP, and this is what we want. Okay, there is at least one element in FP which is not the square of any element. It is a non-square. Okay, at least one element. And we can conclude that by looking at this and counting the number of squares. Okay, how does this help us? So there is at least one non-square element. So let us take that non-square. So let A be any non-square element in FP. And let me consider the polynomial x square minus A, which is a polynomial over FP, correct? Because A is in FP. Now, since A is a non-square, there is no element x in FP such that x square is equal to A because it's a non-square. So x square minus A has no root in FP because no element in FP will satisfy the equation x square minus A equal to 0. So x square minus A has no root in FP, and so x square minus A is monic irreducible in FP. Monic clear, and it is irreducible because it has no root. It's quadratic with no root. Okay, it's quadratic, it has degree 2. So this is a degree 2 monic reducible polynomial over FP. And again, as we have seen before, FP squared can then be obtained as FPX mod the ideal generated by x square minus A, because this is an irreducible polynomial of degree 2. And this field will have size P square because the degree of the polynomial is 2. Okay, so this is a quadratic finite field when the characteristic P is odd prime. Okay, so that is it about finite fields and the cyclotomic extensions, finite fields, and stuff like that. Okay, the final part about this unit is constructions, ruler compass constructions, which we will do in the next video lecture. So I'll stop here.